तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last time we met, we completed the design of a real time clock, and this time we are going to touch upon the test bench. We are not going to write an elaborate test bench, but only to test the basic running of the time as is concerned, and you can try other modes as well on your own. And to start with, we need to declare the time scale, and let us say we want we wish to go for 1 gigahertz simulation. So, for which we need to go for a higher precision here. So, we will make the time base as 100 picoseconds, and the accuracy is 10 picosecond. This we have already discussed a number of times earlier, and you also have a clock period by 2 declared as 5. The basic unit is 100 picosecond. If you put 5 here, it means 500 picosecond, and this is on time, and likewise equal number will be for the off time of the clock, and total what you get is 2 into 5, and that is 10 into 100, which is 1000 picosecond or 1 nanosecond. So, if you take 1 nanosecond, it is nothing other than 1 gigahertz, and that is how you arrive at you fix the frequency in this fashion. And next thing we had to do is we had to include the actual design, which is rtc_alarm.v. This is a design file, and we need to declare the present module, which is the test bench, rtc_alarm_test. This is the nomenclature we have been following all through, and we need to declare the inputs and outputs even on the test bench. And as you recollect, we have used reg for the inputs in the test bench, and wire for the outputs once again in the test bench, which is different from what we have been using in the design. So, we need different inputs such as clock, reset, and run set switch. This is time stopwatch, then up down count mode switch, and then hours, minutes, seconds, push button switches, as well as push button switch for start and stop. And we also need different switches such as alarm read or set, or alarm off or on, then 3 different switches for the 3 alarms that we have, and I stands, as we have seen before, is for the input. And as far as the test bench is concerned, we are not concerned about or alarm etc., which we have used in the design, because they are all internal signals. And as far as the outside world is concerned, it is the I which is the actual input, or display will be the output anyway. Display 1 through display 6, and each of which is 8 bits, and we have seen that ABCD is the order, A is the bit 7, and decimal point is the very last 0 bit. And we also have 2 more outputs, that is beep as well as timer out. and this is what we have used for setting a particular output when count matches in the either in the up count mode or down count mode, and beep is the square pulse which we create in order to switch on piezoelectric buzzer, and buzzer will have a continuous sound, and when you output a square pulse switching on and switching off, you get a beeping sound, and that is why we nomenclature it as beep. And note that in test bench we need to declare all the outputs as wire. And next is we will instantiate the alarm RTSC alarm design module, and that is this here, and instantiate just once. This is like any other IC that you give instantiation there, and we declare ports by names, and clock, reset, and I run, set, time, stopwatch, all these are the input, various inputs, down, up, then hours, minutes, seconds, there as well as start, stop, push button switches, and then alarm, read, set, alarm, off, on, and the 3 alarms that you have. And note that we have used the very same name even inside this. This implies the module name is within the design module, this is the name, and in the present test bench these are all the names. Since both are same, we have declared it as wire, which actually means these symbols as such. And these are all the 7 segment LED outputs for display 1 through display 6, and beep and timer out also will have to be declared. So next thing that we do is apply stimulants, and in the form of various inputs, and when you for that you need an initial block, and that is the begin, and there will be a corresponding end at the towards the end of this test bench. And first what we will do is we will initialize clock to 0, then reset, we will apply the reset pulse immediately. So, and perhaps after 100 units of time we can start the real work, and some more switches are also initialized here, and though not necessary at this point of time, and similarly the hours, minutes, seconds, start, stop all have been initialized to an inactive state, and the active state is start, stop, for example, must be 0 if you mean start has been pressed. So that is to say that it is in start mode if it is 0. Right now it is in stop mode, and all other switches such as alarm, read, set, alarm, off, on, and the individual alarms are all in the inactive state. And after 100 units of time, unit of time here as you would notice is 100 picosecond. We have declared using the time scale earlier, and 100 into 100 picoseconds will be your that is 10,000 picoseconds or 10 nanosecond will be the actual application, starting of the real time clock. And you would notice now that reset has been taken to inactive state. This active low is the 0 means active low, and now we are making it inactive so that we can start the design working. And we also have a run set, and let us set that particular to run as well as to time. So that is what we mean by this comment, run time mode, and so that we can check only the running of the normal timing. And after quite a long time, we would like to stop. Now let us analyze why it is 10 millisecond as commented here. Say we know that it is 100 picosecond, so 100 2 ciphers are there, and you have one more 0 here. So if you knock off this 0, what you will be getting is nanosecond, and if you knock off another 3, you will be getting microsecond. If you knock off further 3, you will get 10 millisecond. So 10 is, that is how you account for 10 millisecond here. And as usual the clock will have to be toggled. We use an always block, and clock period by 2 after this much time, that is every 100 picoseconds, what we do is invert the clock and assign it to itself. In other words, we are toggling to get a free running clock, and this ends the test bench. So now what is to be seen is the actual user constraint file, and put the following in a separate file, say rtc.ucf. You can, having named it as rtsc_alarm, you are free to do give the same name or any other name. So for brevity sake I just put RTC there, and locate it in, preferably though not mandatory. So, there is no compulsion for you to locate it in the same folder, and but it will be convenient if it is located in the same folder as rtc_alarm.edf, which was created by using the simplify tool, and that is a synthesis tool. And this is the UCF file. From here onwards you will have to put in this rtc.ucf file. This UCF file is required in Xilinx place and route when you wish to get the bit stream. Bit stream will be in a .bit file by the same name rtc_alarm, which is the design. And net clock location is what you use for different varying signal. For example, for clock you declare it as a net here and then assign the pin here. So, for example, clock is assigned 89 pin in the XCV 800 device, which we have used on the board, FPGA board that we have used even for the traffic light controller. We are going to use the very same thing, which you are going to see a demo shortly, and these are all various pins for all the inputs. First here run, set, time, down, up, then hours, minutes, seconds, start, stop, and then alarm, read, set, alarm, off, on, and you note that the pin numbers are different from each other, and you have 3 alarms 1 through 3, and for the output also you should have, and these are all the names of these inputs and outputs. And here you note that you need to do bitwise, because there are 8 bits. The system cannot do it all by itself. You have to assign every bit unique number, and note that these numbers are all not in order, and so it all depends upon how you have connected your extension port from the FPGA board, on the FPGA board. And likewise we have 6 displays totally. Display 2 is here, then display 3 is here, then display 4, then followed by display 5, and then finally display 6. And in addition to this, we also have 2 single bit ports, so you need only 1 pin to be assigned, whereas these are all 8 bit output port displays, each of that. And timer out is just a single pin, and that is assigned 162. P is also mandatory, you have to identify it as a pin. So, next we will go into the actual simplify results. So, you can see the usual reporting here, Verilog syntax successful, then top level is the RTC alarm, then synthesizing display ROM as well as the actual design, and this is the performance summary that you have here. And slack means how much time, free time is available, so that you can jack up your speed if you desire. For example, it would be enough if you run at 20 megahertz instead of 1 gigahertz. So, I have also told cautioned you that in simulation you can run at any gigahertz, and but after place and route it will come down drastically. For example, it has come down to 42 megahertz. This is the highest frequency that you can run. So, it will be a misconception and you will be misguided if you just simulate at 1 gigahertz and jump to the conclusion that you have achieved 1 gigahertz. That is totally a wrong picture. Only after Xilinx place and route you will know the true picture, and even synthesis or simplify also will not reveal the exact frequency of operation. You have to go for the Xilinx place and route, which you are going to see next. So, here in simplify we had requested only for a 20 megahertz operation frequency, and it has reported 42 megahertz. So, this corresponds to 50 nanosecond. 20 megahertz would correspond to 50 nanosecond. 1000 by 20, this is the shortcut for you to compute how much nanoseconds, as we have seen before, and this will 42 if you take it will corresponding to this, how much is the estimated period is here, and if you add this to, what you get is this, because 20 megahertz is the actual thing that we want. So, the device that we have used is XCV 800 HQ240-4, and I think this is the highest speed in this particular package, and what it reports here is the primitives that have been used in the FPGA. These are MUX then and exclusive OR, once again mugs, then flip flops and so on. How many of them have been used are listed here, followed by input buffers and output buffers that have been used in the design. And finally, you have a report of how many LUTs have been taken by the design. It is just 3% of the total device, because we are dealing with nearly 900,000 gate, and this one has taken away only 681 LUTs. Just remember 681. We will cross check this figure, and it was 42 megahertz earlier, and let us cross check with the Xilinx, and it says mapper successful. With the Xilinx results, let us make a comparison. We have already seen the navigator for Xilinx using that 6.19 version. Both the 6.1 and 6.2, as I mentioned earlier, is basically the same, not much of a difference. And design it reports is the RTSA alarm, and the input for this Xilinx place and route is the RTSA alarm .edf file, which was created by the simplify tool, and that is the synthesis tool. And it reports, you do not have to specifically mention all this, because this EDF file itself will communicate to place and route tool what device has been chosen, and so on. And you can see precisely the same report here, and once again the target reported here, and it also report there are no neither errors nor any some warnings are there. I am sorry, no errors anyway. The warnings you will have to look into very carefully. And what is the logic utilization? There was nothing wrong with the warnings. It was only reporting that some bits are at 0, therefore it has optimized and so on. So next is 4 input LUTs 641 only have been used. This is the report of Xilinx place and route, whereas it was 681 reported by this synthesis tool. So synthesis tool is only a rough idea it gives, whereas this place and route tool will give you the exact one, because this is the actual FPGA vendor's final tool run on that. And it also has slices reported and how much it is reported there. And I think it was a different here. 4 input LUTs, why is it reporting? Okay, it is same, but there is some discrepancy it appears here. I am not clear about it, and you will have to find out why it is. Okay, anyway it is very close, but this figure is the total number on the device. And finally, it also reports total equivalent gate count for the design, which is nothing but 6721 gates, and in addition to this you need for JTAG IO gate count for IOBs. So if you want JTAG communication for downloading bit stream and through your parallel port of the computer, so you also need this many gates, additional gates, and in total it is hardly under 10,000 gates that you can have. And finally, it reports on the maximum frequency of operation. Earlier it was some 41.2 or 42 point something reported by the simplified tool, but what is reported by Xilinx is the nearly 40 megahertz. So very close to that. And it also reports that DRC has been checked, and it is saving the bit stream RTC underscore alarm.bit. So we have an assignment, but before we come to the assignment, let us have a demo of this, and prior to that let us have a look at the waveforms for this design. So let us say to start with, we have been running the frequency of operation is 1 gigahertz. 1 gigahertz would mean 1 nanosecond. So let us see the clock. First one is showing the clock. I will zoom it up a little later. First let me explain. You can see the clock pulse there, and if you take this one, for example, if it is 10 here, and the next clock appears here, this is a falling edge, so it is 1. So if you take rising edge also, it will be same. You can see from here, so rise, it starts from here, this is also falling edge, it makes no difference anyway. And you see that at 10 nanosecond we had taken as 100 units of time, after that only we start the real operation, and then reset was which was active here and is made inactive, so that the normal operation starts, and simultaneously what we do is we set it to run mode as well as time mode. This is run and time, so it is set to 1 here, and we should also set alarm read set to read position. You should not put it in set mode. If you do this one, you will not get the display, and it will freeze at 0. So you can notice that by changing your test bench. So this will have to be, remember that all these 3 will have to be 1, that is run mode, time mode, then alarm in read mode, and this is mandatory in order that time may run smoothly, and this happens at 10 nanoseconds. 10 nanoseconds because we have taken 100 picosecond as a time base multiplied by 100 which we have given after 100 100 units of time. So that gives you 10 nanoseconds. So this waveform is for that, and zoomed version if you want can just see here. So that is the clock, the right clock, reset, run, set, time, stopwatch, alarm here. You can see that all of them are 1, and at the time of its working. So the cursor is somewhere here. So after it has started working, so that's the point there. So you can see here. So every one clock is this. So if you go to the time base at the bottom, you will see that it's 6 to 7 nanoseconds. So this is 1 nanosecond. In other words, it is running at 1 gigahertz. Although it's running at gigahertz, what has been reported by Xilinx place and route is 39 megahertz. So it should not exceed this time. And another point here is, and we have a display here, and these displays are basically from the counter 1 through counter 6. They are all zeros to start with. So naturally you should have it reflected in the display. You remember that displays are all of them, you can see the same thing pattern right up to the 6 here, and if you analyze this one, these are all nothing but A, B, C, D, then E, F, up to that all are 1. So that means these segments are on. In other words, it is nothing but 0. So this one is the G segment, which is the center segment of the 7 segment LED display, and this is off. So naturally it will automatically display 0, which is in agreement with the counter 1. Through counter 6 all have been the same thing. So when you get to the fag end of this waveform, you will see differences reflecting counter 1 on display 1, counter 2 on display 2, and so on. And so we will go for the next waveform here. So here what you get is the total entire cycle completed. So the real time clock has run right from 0 through 1 up to 2. This one is right up to 23. So we have 23, 59, 59, 23 hours, 59 minutes, 59 seconds, starting right from 0 here. So these are all too high, we cannot notice this here, but you can notice this 2, 3 here. And once again, if you see this ABCD display, I mean, we'll with the next waveform we'll see, analyze to see whether it is tallying with the counter 1 and so on. This is precisely what you are going to get in the next display output, and I'll zoom this before I close this. So you can see that clock, reset, etc., run, set, etc., and you can see clearly 0 through and display 1 through 6 here, and counter going right from 0 through 9 for this is counter 1, this is counter 2. So it goes right up to 9, and once again it goes up to 0 through 9 when the counter 1 is 1, and finally when it is 2, this goes only up to 0, 1, 2 and 3. So after 3 it immediately resets to all zeros. The cursor is here, so when we go into this, we will understand that counter 1 through counter 6 is all 23, 59, 59 where the cursor was, and immediately after that it will be 0, which is the case as this here. And let us go to the last waveform in this And herein what you see is once again the same 235959 appearing here. It has been exploded further. So the last one is the cursor is right there on 2359, and you see that the last value was around 8.64 nanosecond, and after this you can see that all counters are made 0 here, and you can corresponding display you would notice that center G segment alone is 0, decimal point is of course 0 because we have not used decimal point, and all other segments are 1, that means it is displaying 0. This is in conformity with this 0. Second 0 stands for the display 2, counter 3 for display 3, and so on. So let us take this 235959 and then correlate this counter 1 must be having 1-to-1 correspondence with the display 1. Let us say here A, B, C is 0, just keep track of this, then D, E, then F. C and F are 0, this should mean 2 because that is counter 1 value must be reflected. Let us, I will just draw it for you here. So this is 2 here, and if you take this one, this is A segment, B here, then C is this one, C is 0, that is what we have here, then D here, E here, F here, F is also 0, so you can just see here F then G. So C and F are 0 here, and if it is 3, so what you should have is A, B, C, D, and this is E and this is F. E and F must be 0, that is for A, B, C, D here, E and F, you can see this. This correspond display 2 or counter 2 must be a 1-to-1 correspondence, that must be. This is 7 segment display, and 1 lights up the LED, remember that. So 3 is also verified. Now let us go for 5. So here you see B is absent, this is D, E. B and D are off, that is 0. Let us make sure about this. So that is display 3, that is 5, and display 3 here, and B is off, then C, D, E, B and E, and is it correct? B, C, D, then B and D you can see. So that is why 5 is displayed. And now for 9, so what you have here is you do not have this, this is C, D, E, E is 0. So let us make sure about cross check at display 4. So this is A, B, C, D, E, this alone is 0. Just do not be confused about this 0 because this is only for decimal point. Anyway, we are not using turning on the decimal point, that is why all of them are 0. So this confirms that there is a 1-to-1 correspondence between counter 1 and display 1 and so on, right up to counter 1, counter 6 and display 6. So and you can see that 8.64 millisecond it has taken, and next we will have a demo. See what is shown here is the hardware. You can see the FPGA board that we have used earlier. This is the FPGA board, this is the centrally located chip is the FPGA, and towards your left is the digital I/O card, and note that the cable is going from here and getting connected to the extender I/O port of the FPGA, and part of the cable is here on the left, there is a connector there and another connector here, both are extender which will be connecting to the external world as far as the FPGA board is concerned. That means the IOs are connected there here, and this is the display that we are going to use. This 2 digits for hours, then minutes, then seconds here, and since it is not clear here, the exploded view is shown down at the bottom. Whatever you see there is actually functioning. Right now the real time clock is running here, hours, minutes and seconds here, and notice that there is a power supply. There is also another power supply not visible to your view, just at the rear end here, and there is also a buzzer there. This is the piezoelectric buzzer, and in front of that mic to pick up when the buzzer gets activated, and we will see very many modes and under which condition the buzzer will be activated. And to start with, what we need is a load. So on the system that you see here, there is one GX load. So just click on that one. So it opens this window here, and this window has different bit streams available, which is the result of Xilinx place and route. So, this is for the RTC alarm dot bit, and we I have also made one hours fast as well as minimum, I mean minute fast. This is to help us quicken the demo, I mean to test the real working by speeding up the clock, so that we can see hours as well as minutes very rapidly. For example, you want, let us say we want first let us download this hours fast. With this condition, let us see what will happen. You just hold, do not release the mouse button when it comes to this window, and just release that here. This is the bit stream we had we are going to download, and there is one load button here. Just press this one, and buzzer is also sounding. The reason is at the time of configuring, the counter is all reset. Now you notice that this hours is running fast. You can see it started with zeros, and it's going counting one at a time, and it will go right up to 23 and then roll back to 00. This will check this hours, which will normally take 24 hours for you to check. We have taken hardly half a minute, and so you have seen one revolution complete. So, now in order to check the minutes, wherein this similar thing will be observed with this 2 minutes display, and for that what you need to download is this RTC alarm minute fast, and we will just once again drag and drop it here and then load this. It is downloading that particular minute fast bit here, and it starts with that buzzer was on once again, and I hope it is audible to you. And you can see now this 2 digits just below this, 2 digits are going on one after another, and it will go right up to 59 seconds and then roll back. And so, in addition to this, we have the usual alarm dot bit. We will do the same thing, and we will put it, drag and put it over here. So, you can just observe the minutes going right up to 59 and then rolling back to 0. We will wait for some more time for the next thing to, we will act on this alarm dot bit, which is the normal running in seconds, minutes and hours, which is the real time clock, and we will take it up soon after it completes one revolution. 59 now, 0 here, and 1 hour it has advanced. So, like this you have checked first hours 2 digit whole sequence you have seen, as well as on the minutes. And now what is to be checked is only the seconds, but it is too fast for you to see. Maybe you can see the second digit of the seconds going, and in the normal mode we will see that now what we had to do is download this alarm dot bit, which is the normal mode. So, we are downloading now by clicking on to the load. So, now it is normal time. So, you can see every 1 second it is making the change, and the alarm is on, and it is a beeping sound that, as we have already seen in the design, and this will is programmed for 30 seconds. So, and now what we have to do is we will do this setting for a particular time. Real time is not this correct, because all of them are 0. And now buzzer has stopped after 30 seconds. Now let us say we want to set it to the desired time, and so let us, I will first invoke the time here. We will first set the hours setting here, and it is right here. We have a DAP switch here, and down we have 4 push button switches there. We need to use this on the left push button switch in order to do the setting. So, we will now do the setting as per the system clock, which you see right on the computer, and it is now 12:41, 12:42. We will set it for 12:43. Now hours will be set. So you keep it, hold it so that it runs when it closes by 12 is set. Now minutes, we keep it pressed so that it counts fast. After 2-second delay only it started, and now when it closes on we will set there 43. Now we have another 30 seconds. Look at the system clock there. So now I will count the 35, 36. So after this 42, 38 now right now. So I will count, and our friend will synchronously switch on that start button. So and we will have a look. 51 now, I am counting now, 53, 54, 55, 56, 57, 58, 59, yes now, right. So it is 43, not 4 there, and on the system also not 6, not 7, not 8, 9, 10, right. Some slight discrepancy is there because human being cannot set that clearly, and the control that we have is on this here. So this is the control that we will have to operate. So hours, minutes, seconds is the display there, and these are all the setting. It was put in set mode and time mode. So set time is what we have seen, and using which we have set, and other modes we will see once again come back to this. Now you are seeing that timer running. Next we will take down counting. So we will start now. You set for the down counting, and in order to do this one, what we need to do is we have to put it to set stopwatch mode. We will now set the stopwatch to 30 seconds and see what happens. It is in down mode, and it has been already set by using once again this hours, minutes, seconds push button switch. In seconds we have used, and it was in set stopwatch mode. Now we will start the down counting mode. So by pushing the start button, you can start counting. You can now see after it was started 27, 26 and so on. When it touches 0, it will freeze on that point, and the buzzer also will be activated. So let us wait for some more time. After this we will be taking up the up counting mode. We will use the real time setting for the up count mode. Now just wait for 5 seconds, 2, 1. So you heard the buzzer and it froze there. The buzzer sounds for 30 seconds, we will cut it short anyway. We will set 15 seconds for the up count, and now we will start in order to start the up count mode. So now it is counting 1, 2, 3, 4, and right on the top on the one bar display is there here, and watch for one small segment light up. After now you can see that segment has come. In fact, I forgot to tell you on the down counting mode, then also it came on, and after 15 seconds is over, buzzer has been activated, and it count display has frozen to 15 seconds. 3 alarms have been set for 1 o'clock afternoon, of course, and then 1 minute I mean, and then 1 2. So 1 hour and 2 minutes, 13 hours that means. So looking at the actual real clock that is on your screen right now is 46, 47. When it touches 000, first alarm must come on, and the buzzer also must come on. Just let us wait for this. So the alarm has come on precisely at 13 hours, and it will go on right up to 30 seconds approximately, and after this you will be getting the second alarm, that is alarm 2 has been set, and you can even see on the computer you can see the same time here. So this proves that it has been the timer which we have set right at the beginning has been running in spite of the fact that we went into up count mode, down count mode and so on. And so let us have a look in the meanwhile to the settings just for recollection how you had set. So, we had a run and set, and we are going to wait for this second alarm to come at another 15 seconds. Till that time you see here we have used set stopwatch earlier, and now in order to set alarm we need set position here on, and if you want to, now you see exactly at 1 minute the second alarm turned on, alarm 2. So, that was this one, because using this you can set actually. So, this must be in set position, and you should take it, if you want to set alarm 1 you should take it here, and then it will be automatically set to whatever was there on the display, and which you can advance only in the stopwatch, not necessary. Okay. So, whether it is in stopwatch I am sorry or not, it will go on. So, exactly after 30 seconds the second alarm also stopped, may not be exact, right, maybe it appears some half a second or 1 second delay is there. That is not a very important thing, and let us wait for the third alarm to come, which will come in another 12 seconds. At 13 hours 2 minutes 00 seconds you will you have to get the third alarm. Once again it went on, and for next about 30 seconds it will sound. As I mentioned, this application can be used for patients like epilepsy, and if you do not administer the tablets, if they fail to take the tablets in time, say within half an hour or 45 minutes, they will promptly get fits. So, in order to avoid this one, you can have this particular timer which will keep them warning for say at morning at 8 o'clock, then towards lunch time at 1 o'clock, and then again at 7 o'clock dinner time. So, they should not miss it for long, and in fact you can build in even more sophistication. Suppose they in spite of your ringing in time, suppose they take much more time, and suppose they have dozed off. So, what do? You can continue to sound the alarm intermittently after 5 minutes and so on till they press another button to acknowledge. So, you can, if you want, you can add this feature in your assignment, which you are going to see next. Let us discuss our assignments, rather your assignments, and first assignment is we have used 24 hours clock, and what you have to do now is provide another switch and include 12 hours clock as well. For I will read it out. Modify the Verilog code to display the timing range 0 to 11:59:59. This is the maximum. After this, it has to roll back to zeros. Besides the 24 hours range and other features, you have to retain as it is, and you may use another input and an output available in the expansion connector of the FPGA board for this purpose. I think this is clear to you. And second assignment is, so when you say talk of real time clock, so you have to have year, month, day as well, otherwise it is not really a real time clock. And it should, when you say year, it should at least be for the present millennium, is that right? And so right from 2000 to 2099 you can have. So, you make sure that you have, and for which you need only 2 digits, you do not worry about 2000 last 2 digits alone you need to take. So, and month of course is clear, up to 12 it can go 1 through 12, and day again depending upon whether it is February or January and so on. So, you have to keep track of all the variations in the number of days in the month. So, you have to keep track of all this and then build the whole thing, and basically it is going to be a different counters here, and you do not have to worry about sounding the alarm with reference to any of this. So, let the alarms be as it is, catering only to the hours, minutes and seconds. So, without disturbing hours, minutes, seconds, you should build this year, month and day as well, 2 digits each, and for which you use the same display, display 1 through display 6, and you need to use a different counter, remember that, and that is what we say using the existing LEDs. So, third assignment for you is, I will read it out first. If you are to use the timer for applications demanding timing in milliseconds in addition to seconds, and more often we need for milliseconds, for example, you have a photographic exposure I mean you want to develop print, before that you had to expose the film and inside the dark room. So you may need probably a millisecond resolution onwards. So for which you need timing right from 0 to 999.999. So after dot you have 3 digits, so this works out to be 1 millisecond, the very fag end of on the right. So I will read it out. If you are to use the timer for applications demanding timing in milliseconds in addition to seconds, then we need to modify the existing design, that is obvious. Use appropriate numbers of additional inputs or outputs and provide user presetting to include this feature in your design change. And you also need to have presetting, appropriate presetting. So all this demand additional inputs. So you can use push button switches preferably, and the display shall be in the range 0 to 999.999 seconds. The timing must commence when the user presses the start push button. So this timer is class different from what we are used to earlier, and in that case it was an on delay timer. After the set delay, the output timer out goes high, that is called on delay timer, whereas in this what we want is an interval delay timer. So when you push a button, the time delay starts as well as timer out goes high, and after the delay is over, the timer out again goes low, and that is what you want. Is something like pushing the button, starting the time, and after the set delay is over. For example, if you have set 999.999 seconds, and after that time is elapsed, timer out goes low, and till that time, soon after you push the start button, it went high, and that is what is called interval delay timer. This is what you are required to design now, and on similar lines we have done before. For on delay timer you have to do only thing, logic will have to, you have to incorporate or change it aptly, and after the lapse of the set delay, the output is turned off and the beeping audio alarm sounds for 30 seconds. So this is once again the same thing, and use a separate switch, preferably a push button switch, for presetting or clearing the timer before restarting by pressing start push button. If you if you press the start push button, it should start, and you need to either preset or clear depending upon what mode you want to use. If you use the down counting mode, so you would like to preset. For this you need another input. Say you have for presetting you can have another switch, maybe it's a likely choice would be a push button switch. So you push this one, so whatever was set on the display, let us say 999.999, and that will be transferred to the running counter, and at that point of time, but it won't start unless you push the button, start push button. And after this, otherwise if you want use up counter, you would like to clear to start with. So you can the preset value is inside the preset counters, and just like we had alarm counter separate for presetting them, and here also you can have for up counting or down counting a preset counter separately, and the running counter is different. So whenever you push the button, if it is up counter, let us clear; if it is down counter, let us preset. So once you have preset, it will be cleared, all the display will be cleared. When you push the start push button now, it will start running right from 0, 1, 2, 3 and so on, and till the set value is got on the display, and by that time the timer out will go low, and when you had started it went high, and so it remains high for the duration of the delay that you have set, and after that timer out goes low. The digital timer may be stopped or resumed at any point of time, as was done in the design presented before. This the same feature that we have seen earlier, and let us have one more. This is the last assignment for you, and I will quickly read this first. Lots of power is being wasted in offices, factories, institutions, especially during lunchtime, etc., which can be easily avoided by installing a real-time clock such as that we have designed, of course needing quite many changes. We need to do quite a lot of changes in this. Include in your design change 4 outputs for switching on or off 4 different electrical circuits that power lights, fans, air conditioners, etc., as per the following schedule as an example. For example, you want to set from Monday through Friday, let us say, you want to, if it is a factory or an office, it starts, starting time will be 8 o'clock. So, and then you have to switch on one of the circuits. I have mentioned 4 different circuits for lights, fans, air conditioners, and one more some other load. So, independently you will have to be in a position to set all this, and once again it is not merely Monday through Friday, it has to be right from Monday through Sunday, all you will have to cater to. And it's as an example, what has been shown is only two pairs of timing here. So, it will be on at this 8 o'clock, then off at the lunch time, and after the lunch time is over at 13 hours, you have to switch on once again and switch it off towards the end of the current shift. And so, this is not adequate. I want you to add 2 more. For example, you need a tea time at, let us say, at 10 o'clock, and let us have a break for 15 minutes or 20 minutes. So, it should be programmable, because you say on time is this, off time is this. So, accordingly you can do that. And you are required to do, in addition to this, 2 more settings, tea time for morning at 10 o'clock and 14 hours or something, whatever you choose, towards evening. And you must facilitate the user to program for any day of the week, any time, and up to 4 different time settings, each for switching on and switching off lights, etc. This is what we have said. Each of the power loads must be individually programmed, and this has to be individual, and each must be 4 different times. Provide an additional switch for overriding the automatic control to switch on all the 4 circuits when the occasion demands. You should also have a provision which will turn on. For example, it was a holiday and timer would have not switched on. So, what do? There must be a overriding control switch there in order to switch this. So, you can veto the automatic control that you have. Are you clear with this assignment? If so, thank you.